comes from the fellow, the new fellows of the Institute for Mathematical Sciences of the Humanities. It's a great pleasure to introduce the newly minted fellow of INSA from Universidad de Santiago de Chile. And he was speaking about Eigenvarieties and arithmetic.
Hello, thanks a lot for the invitation. So I will speak about eigenvarieties and arithmetic. Eigenvarieties are varieties, certain varieties that I will try to introduce and to explain the connection with variety arithmetic. Okay, so let's start. Okay, I will break the protocol after the introduction, and then I will try to explain some theorems in part 2 and part 4. Explain a little bit what are the invariants. So to give an idea. Okay, let's start. Let's start with the absolute values of the rational numbers. So you have one natural kind of value, which is given by the norm, or the absolute value, the usual one. But there is another family of absolute values which are much less, a little different family, which is depending on prime by prime. So you pick up prime, your molecule, and you find very close with the absolute value, which is given by this formula. You look at the rational number, you look at the power of p in the position of primes, and you just put the minus. Okay, that gives you a mixture of rational numbers, which is different from the other one. And in fact, there is a result for a plot in 1916, which is probably the only absolute values of the rational number are for these two kinds of examples, where there are no more absolute ones. Okay, so when you look at this, then you can have the following picture. So you start very interested in this set of rational numbers. Are going to be problems with here, and we will say global. You can work somewhere locally. And some two different settings. One is the Archimedean one, given by the completion of respect to the first norm. Absolute value, I give you the rest of the real numbers, and then this is not algebraic close. You complete and you get the rest of the complex numbers. And you can do the same, you can play the same game on the second equation. You fix a prime, you complete, you get the p-adic number, which is kind of the parallel of the real number. Then you repeat the same structure, the same game, you complete the algebraic closure. But now to practice this is not complete. Okay? And if this is big, and you complete and you get something else called the base field, which is okay, so you have these two situations, and my work is taking kind of mixing both situations, but we use a lot of geometry in this side, and non-Archimedean geometry. That's where you live the eigenvariety. Yeah, that I will explain. Oh, okay. So let me point out some difference between these two settings. For example, if you look at the real numbers, you take the unit ball, that's just the interval minus 1, 1. You have no algebraic structure there, but if you do the same on the p-adic number, you get the p. This is where it's a ring. It's a complex ring. So you look at very different situations, different situations involved. Okay, so let's introduce some notation that we use during the talk. So first, you put all the completions together, and you get something called the adherence of field that appear already in some talk. And you cannot take just the product because it's bad to take. You think, oh, I forgot the real numbers there. Oh, sorry. So here you need to put the real numbers too. Okay, so okay. And you put this condition here in order to get a locally compact group. Okay, so you have Carnet group and you can do stuff. You can do the same that. Well, I can probably put it in the opposite. Okay, if you change the you put here. No, sorry. If you put R, you move there, everything is correct. Sorry. Okay, this is the defined concept. Okay. Okay, these are annotations, but let's fix a prime feed. And my work is mostly about the study of p-adic deformation of certain global objects and collection of arithmetic. So this certain of global objects are called automorphic representation that I will explain in more detail in some moment. And I think that the type of deformation that we are considering here is a p-adic one is a local study as deformation, it's local study of certain varieties which are these eigenvarieties which are moduli spaces of this automorphic representation that belong to the world of harmonic analysis. Okay. So the goal of my talk is to explain what's mean all this word that I will say here, give you some idea of what I'm saying. And second, give you experience of theory and proof. Okay. So the first word that appears here that I'm saying, of course, is automorphic representation is global object. As I told, global means also Q or p-adic. Both for me are global. Okay. So when we say when we want to when we study algebraic number theory, what we mean is to study these sets, this ring, this field. The study this field is very mysterious, and let's involve algebraic number theory to say something about them. We realized about 200 years ago that it's better to study the God of physics because you can say more stuff. Okay, and we study the movements of this field, which is this group that we call the God group, and it's a set of homomorphism of ring cells, of fields, of this ring stuff. There is a finite group, it's a composite of natural topology. And we study this group as okay. So to study groups, so we arrive to the study representations. So we study groups, we study representations, and okay. So that is the kind of the goal of Daniel's program to describe the representation of this group. You need to put some adjective to don't have wide representation, so you have a big one. The idea of this Daniel's program is you have this color representation, and you want to describe it in terms of another object, which are these objects that I mentioned before, which is global object, or I call it as a automorphic representation that belong to this harmonic analysis. Okay. And I will give some ideas of what's mean all this. So first, this is parameterized by a inductive group that we fix now for here. We fix the group, and we have two sides. One side is the arithmetic one when you have the arithmetic problems. So arithmetic problems can be described in terms of color representation. Okay. So at first you need to take presentation of these groups. You have an natural topology, so you need to respect this. Okay. That is not enough because you have already, because even with this condition you have a lot of representation. You need to ask more, and something that's an objective that's called geometric making. That's from some alpha some varieties. These are, and you need to have more objective, but that's you can idea what's the arithmetic side. Okay. The other side of this Landmark program in this particular case is the analytic side, and these are this order of global objects which are called the automorphic representations. And to have an idea what's mean that is the automorphic representation of GA, and you can think about it as like a piece of this Hilbert space. Okay, so as I told you, the definition of A is to have a locally compact group, and this is locally compact, and the question has a natural coordination, so you can give That's have a natural meaning to be a Hilbert space. Okay. And you have a natural option of GA, and you can think about automorphic representation as a irreducible pieces of this GA. But you need to make a little bit something at infinity. It's not really a representation of GR, but it's a kind of GK moduli. Okay. But you can think as a GK reducible component. And these are the two sides of the Laplace program in this situation. There are much more general conjecture and you've got another Laplace ideas in different other contexts, but for this is what I'm using in my research right now. So this is a picture that I found on the internet. It's very nice. So you have two islands. It's a very nice cartoon, I think. Here you have kind of the where is it? Yeah, here is the arithmetic side, you can say. Okay, where you have problems and you want to be resolved. And the Laplace program gives you translate these problems in terms of automatic representations, where you have plenty of methods. You have here, you have algebraic topology, you have some algebraic representation theory, you have a lot of tools and you can do tricks and you can expect to do something about the problem you have here. So one kind of problem that we are interested is about the L functions. Okay, these L functions are the natural. So one example of a function is the Riemann zeta function that we all know. Well, that's enough for explicitly in the middle call, but the difference is a sum of terms. You can talk. I can give you this problem. This. Okay, this is the Riemann zeta function. You need to take care of S, bigger, the real part of S bigger than 1, and that makes sense to have a multiple function. Okay, that's the prototype of function. But in the situation that I mentioned before, they also have that function attached. And we expect that this reach to be well behaved, so we respect them. So, for example, if you take GGLN, your automatic representation of a natural function which is a standard one, and the other representation you have a precise receipt by the linear about what's in the L function. It's not really a simple thing at sum, but it's also a product. So it's better to think about this as a product, about all the prime numbers and one. This okay, so the construction of this function in this situation is to describe precisely the error is for your factor. And you can get that function in both cases, and the Laplace programmers should respect them. So Laplace program have a lot of advances already. What we are doing in the mirror set, if a particular set is trying to use these advances of the Laplace program to say something about arithmetic. Okay. So, because in fact, some precise conjectures that appear in arithmetic are described in terms of, you look at the special values of these functions, these L functions. For example, one important problem is this BSD conjecture or Proctor conjecture. When you look at the values of, you take the integers here, and you look what is that, and you want to describe it. Okay. But you can translate that using Laplace program in terms of automorphic terms. So there you have plenty of methods that you expect to do something. And in that situation, when you translate stuff to the automorphic setting, one important tool is p-adic deformation, which was the mentioned at the beginning. So p-adic deformation, you deform everything p-adically. It's something that sometimes in some situation you have no this freedom to do it in the Archimedean situation. Okay. So let me show you some examples. So this GL2, the Hilbert modular forms, we have one theorem that I would like to explain to give you an idea of what I mean what I said before. Okay, so you can see that. That's perfect. Okay. Okay, so this is a precise equation which we will fix a precise group G. Okay. Let's fix a totally real number field. What's mean a totally real number field? It's is a finite extension of the field Q, such that when you look at the window morphism in the complex number, you have to stay there inside of the real number. That is totally real number. So, okay. And the group G that we will consider will be you take the Q or X and you go straight to Q. That is our reductive group. Okay, so we will consider the Laplace probability situation, and we have a lot of different proofs already available to use. So you can translate problems in other terms, from other terms in terms of the most representation, and you can try to prove this. One interesting thing is about F functions. So take an automorphic representation, which here you have two more adjectives, which is the first one is capital, which means that the automorphic is in terms of this function where this is okay. So let me remove this. Okay, so the space of function where the automorphic representation live will behave at the boundary in some sense of this quotient where it's defined as a will be zero, will be vanished on the boundary in some way. Okay. So that's mean capital. So you need it's a condition on the function where it's realized the automorphic representation. Homological is that something I would like to give some ideas, but it will be in the next section. I will give you more ideas what to mean that. That will help us to explain the construction what to mean and Eigenvarieties. Okay. So let's keep homological now in not precise, but we will come back to that. But let me learn some homology out here. Okay. So the object that we're interested to study is the L function. Okay. And this is a holomorphic function in S. Or it's an entire function, okay? That because fidelity implies that it's entire. But if this function is not holomorphic or all the functions, it's have a pole that is equal to 1. But the automorphic representation behind this setting is not capital. So that is the reason why here you have holomorphicity all the time, but here not. Okay. You also have a functional equation like the reductive function. And the center of symmetry of the functional equation is S equal 1 over 2. Also, the functional equation relating S and 1 minus 2. Okay. And this is proven in the 1970s by Jack and Ernest book. Okay, so what we want to do, I want to spend some p-adic version of this and to study some special values. So, okay, so fix integer upright integer equal to 2, and we have a p-adic version of this complex of functions. So that is not trivial. So in fact, the construction of p-adic version of complex function is a very active field. And to find a general construction for a lot of stuff. Very general construction for automorphic representation is something very important. Okay. And part of my work is trying to do that for more general group in the representation too. But in this case of DL2, the construction is start with Marin in 76, Dabrowski in 515 in 94, Mock in 2009. In my thesis in 2013, and Barrera Salazar in 2017. So, in this last two works in my thesis and Barrera Salazar, the construction is a different construction, it's a very homological construction, and was very useful to study the p-adic function. These other ones are like for by interpolation that you can say, but these ones are using the homology, or the homology, and allow us to study the p-adic function to give to say something about its following theorem. So before let me tell you that the p-adic function is connected to the complex of functions, some values. For example, when you evaluate our p-adic function S equal 1, you see the connect is connected to the complex of function and the center of symmetry. So, and these values which always is interesting, you have a lot of conjectures about the order of vanity, for example, the complex of function of S equal 1 over 2. So you expect to have also the same conjectures at s equal 1 for the p-adic function. But there is a very new phenomenon that you have an extra vanishing. And that is something that occurs in a lot of situations, that is extra vanishing. And it's a new phenomenon that we still are trying to understand how we explain it. In this particular situation, we have the following theorem that we proved in 2022 with Dimitri and George. What we prove is assume that the automorphic representation is not critical in what call it spherical P. So these conditions, I will give some more details in the next section, where I need to get that. I don't know. The first one is homological, and now this, for example, I will give you more details in the next section. And assuming that, we will prove the following. So the extra vanishing, we understand now that is given by the ramification of the automorphic representation in some primes. As we are working over P, we're periodically working, so you consider just the places over P, such that the automorphic representation is standard. So what means standard? So in our representation theory, a natural way to produce automorphic representation is taking induction. In this case, we are moving GL2, we take induction from GL1. It's a natural way to construct automorphic representation. And to be explained, it's like it's a piece of the induction from the trivial representation. Okay, that means standard. Okay, and we are understanding that the extra vanishing, this is connected to the ramification of the representation, and this standard representation that's very particular. Okay, in this situation, what we prove is that the order of vanishing of the p-adic function of s equal 1 is bigger or equal than p. Okay, and we have a precise formula for the derivative p times. So if you look, here you have the derivative, if you rank a p, you have the value. And that shows you the new phenomenon, you see the extra vanishing. You are connecting the derivative with the element. Okay? Okay, well, of course, this is 0, so this we call that 0 equals 0. Okay? If it is not 0, you have a nice formula. But I need to give you some what mean these two numbers. So the first number is contain major invariant attached to the color representation attached to the automorphic representation. So what's mean that is this bridge that I explained at the beginning, this Daniel's problem. In this situation, you have the construction, you have the automorphic representation, you have the color representation, the bridges, you can walk in both directions. And you look at the color representation and you restrict to the composition group at P, or at the place over P. And you play with Copier theory and you get some number. And that is called the Eigenvarieties. So this number is very mysterious. And we don't know if that is 0 or not. So in the theorem before, that if that is 0, we expect there is no 0, but still, we don't know what to do. And this number E is not it's not a difficult number. It's a familiar factor, something on this side that we modify a little bit. Okay. But something more about this number is that if you take x equals q in the theorem, that is a theorem that people call the Saint-Étienne's theorem. Saint-Étienne is a small town close to Lyon in France. And the professor from there proved that this number is not 0 when x equals q. So for general f, it is not true. That belongs to another field, which is kind of transcendental numbers. And we are using that. So you don't know what that is. Okay. So the proof is based on p-adic deformation of negative involved. You deform the automorphic representation, you deform p-adic with the color representation, or you deform p-adic with the F function. The p-adic function that you have involved, you deform everything and you mix and you get the formulas. So that is the first time that this method is by Greenberg Stevens in the 93. And we were generalizing it and using new information that we had. then there's a new development about the eigenvarieties. Okay, when p corresponds to an elliptic curve, which is a very particular case in the theorem, this theorem was proved by most and it's zeros. Okay. But the methods are very different, very different to this one, and then we have some connection that. Okay, so what first I take advantage to say that if you take with the center of this value 0, so you want to try to say something to take more derivative, for example, to say something. And there's a work of a PhD student that is working on it now, and following the works of Bertolini, Darman, and Mock. The same work here. Okay. And I would like to tell you also today that with Antonio Cochi, Santiago Molina, and Victor Roger, we are working on the connection of, in this setting too, that the L values to the twisted elliptic curve. So you take an elliptic curve of F, you twist, and you want to say what is the order of vanishing of the F function have a relation with the rank of the model by group. Okay. Now I can, so I will, so I mentioned p-adic deformation all the time here. In the proof of the theorem is p-adic deformation. P-adic deformation is the local deformation is the local geometry, study the local geometry of some moduli space. So here I will present you which is the moduli space that we are considering. I'm not really maybe I will give you some ideas of what it is, okay, or how you construct it. Okay. So what are the eigenvarieties? Are geometrical objects encoding p-adic deformation of automorphic representations. So it's what I say till now. So geometrical object. So the geometry that we are using here is the ridge geometry. This is a non-Archimedean geometry. Okay. And these are moduli space of p-adic automorphic representation. So here there is an objective is p-adic. Automorphic representation, I would say before, but now I'm adding p-adic. Okay. So the moduli space will parameterize a lot of objects, but some of them will be real automorphic representations, global objects that we are considering from the beginning, but others no. Okay. So the variety will have a lot of points that we are global in some way that have some arithmetic meaning, but a lot of other points are really transcendental, really p-adic. And yeah, we want to understand what is happening. So that will be the subject of the last part of my talk that we will work on there. But before let me introduce this space. Okay. To construct this space, there are a lot of different constructions using coherent cohomology of some similar varieties, using group cohomology, but the approach that I choose because it's well connected to L function, of the alpha function, is using a similar cohomology of this object arithmetic manifolds. Okay. A similar cohomology is very small, but arithmetic manifolds I need to introduce a little bit what is this. Okay. So let me give some ideas of what is this. So before we introduce them, I would like to take advantage to say that the eigenvarieties are geometrical objects, and to study the singularities of these varieties is very important in arithmetic. But a lot of problems, works of Darman and Bossi, Bond, having very deep connection, for example, to the explicit classical theory, are connected with the similarities of these varieties. Okay, so I will try to say something more about that. Okay, so let's explain a little bit what's so we want to give the idea of the formation of the automorphic representation. So the way that we should do it is having one parameter of this automorphic representation and moving this parameter. And this parameter is the weights. Okay. One of the most representative of two parameters, the level and the weights. These two parameters, you have more than these two are important. Other thing, the level and move the weight. So what I mean by that is, so we fix a reductive group over Q, which is split at P, and we fix a Barrera Salazar of G and a maximal torus. Okay. The weights of the automorphic representation of GA are simply its algebraic character. Or algebraic character of T. These are the weights of the automorphic representation. So the idea is to put these weights in a this is kind of the same, for example, for G plus GL2. P will be the torus GM. This is just Z plus Z. Yeah, so it's really straight, you don't expect variation there. But you can put it inside of a space that there you can expect to move this. So the space where you expect to move these weights, the weight is this one. It's the weight space, which is a rigid variety of activity, parameterizing a continuous characteristic. Okay. So this is you have much more points here than here, you know, because this is kind of Z cross Z, and this is kind of this rigid this. So you have now the idea of variation. And something good is that, okay, so this is when you space contain the classical weight because any algebraic character you can just look at the points of the algebraic character and you get a point in the rigid space. But there is something very interesting that is the image of this classical weight theory is very dense. So now you see, now you obtain a space which is a rigid variety, which is the analytic non-Archimedean geometry, which is really a variety, and you have inside a dense set of points. So now it makes sense to us if we can form the automorphic representation over this W. Okay, these are the Eigenvarieties. So I will give you some ideas of the construction now. Yes, and so because I told you that I will do the construction using arithmetic manifolds. So let me introduce what are the arithmetic manifolds. So the arithmetic manifolds are depending on a level, and this level is an open compact subgroup of GAF. So AF here you have no infinity. So this is the level of an automorphic representation is mainly okay. So you take the automorphic representation, for example, you have an action of this DAF, sorry, it's acting here because this is a real representation. So at infinity you have some fraction. So the level is some group such that this is non-zero. Okay. Some groups, so you can take some optimal groups in some way. These are the levels of automorphic representation. Okay. Okay. And the arithmetic manifold is a real manifold given by the following equation. So is you take the identic points of the group, you take a double quotient on the left by the rational points and then diagonally. And on the right, you take the quotient by the level and some information on infinity. You see, because if you don't, yeah, some information on infinity. And this K infinity is a subset of the group of the real points, or there is a maximal compact module of the center. And this is the real manifold. It's very explicit definition. And this is a real manifold. Okay. Maybe this like this is not very clear, but for example, if you take G equals GL2 over Q, for example, and you take K, this take this case 0 n, no, that's very common to see, which is take any bigger or equal than 3, for example. Or any n more. So you take, these are the gamma in GL2A O, no, AF, okay, such that they are integral in fact. So if you want that below the product of all the P, set L, I would use L, you don't go to P. Yeah, it's really the integral finite adels, you take the integral 2 points, and you have the condition that when you look, okay, so modulo, you take this modulo n, okay, this will look like something like that. You have 0 here. So this is a precise level that you use to speak about the conductors of the automorphic representation of this equation. So it's not very random because there is a parabolic behind the Barrera. The arithmetic is behind, so it's really with that. Okay, that is the level that you choose, for example. And when you consider this manifold, that is in fact the upper half plane divided by this congruent root. This is isomorphic to this with gamma 0 n. The matrix of SL2Z, which are congruent to 0 modulo n. And this H is the upper half plane. So if you look at this basic description, then you realize it's a two-dimensional real manifold. In general, you have real manifolds that, in general, for example, if you take GL3 or GL4, this is not an algebraic manifold, right? In this case, yes, it's a Riemann surface and have an algebraic structure. But in general, no. For example, for GL4, you get a real manifold of dimension 9. So you have, okay, these are the real arithmetic manifold that we are using. So we are considering the cohomology of this manifold, and the cohomology will take some great coefficients. And the idea is, as I told you, we fix the level with this k, and we move the weights. And in some terms about the arithmetic manifold, you are moving the coefficients. And the coefficients are given by this. Take a weight, it's a character. By general theories about the algebraic root, these dominant weights, dominants mean some relation with the Barrera that is the beginning, so you can ignore it. And there is a rejection between the reducible algebraic representation of G with this kind of weights. This is a very general theory of the dot group. Now you can take this coefficient, this is half an action of G because it's a representation of G. So you have you can get a shift over this manifold. Then you consider the cohomology of this. And you can consider this cohomology given by a singular cohomology, just singular cohomology. And okay, but so now I take advantage of say this delta. The automorphic representation is called homological when lambda is appearing in this cohomology. So what means appear is that automorphic representations have a lot of local information. The numbers that appear for each prime. And here you have an action of the cake operators. You have some natural correspondence acting on this cohomology that give also numbers. So you ask that this sequence of numbers appearing in automorphic representations appear in this cohomology. And that's called. Okay. So the construction of eigenvarieties starts with pair in 72, I think. But here it was in no capital case, but in the capital case it was a very important work, two works of Ida. As it's given in 2008, Urban and Francis and with Chris William in England, we kind of improved this construction in some direction. We consider more general eigenvarieties We are very good situated for arithmetic purposes. Okay, so the theorem is that there exists a rigid variety endowed with a local finite morphism. This you need to think. This is the moduli space that we're interested. Okay, and the point should be automorphic representation. And then the morphism take an automorphic representation as the weight of it. Okay, that is the meaning of this morphism. That's the weight map. It's locally finite, which is interesting. And the points of this eigenvariety correspond to system of eigenvalues appearing in the cohomology. But now there is a very subtlety. Oh, here I forgot. Sorry, so I forgot the thing. So if you take a full point x here, okay, call lambda the units, which now can be a p-adic the weights. That's something very transcendental, p-adic weight. And for this way, you can construct instead of an algebraic representation, now you consider something bigger, will be a set of these local analytic functions, or you can take dual optical, you take distributions. Okay, that is much bigger space, and you take the similar cohomology again. So okay, so the points here are parameterizing eigenvalues appearing here. Okay, that is the idea of the eigenvariety. So then you have what is construction. So you take this kind of spaces, you, for example, here, and you can take this correspondence up to here, so that you can take the algebra generated by them. It's a ring, it's an algebra over this field we are working, and then you can take the maximal spectrum of this big algebra. And then you glue them and you get this rigid variety. That is the construction. Okay, and something that makes sense that I was saying that a moduli space is that when you take the weight to be an algebraic weight, then when you take the inverse image by the weight map, you get some set of points here, which will be finite because it's not finite. No? And in fact, these points should correspond to real automorphic. Okay. If the point lambda is in W is not algebraic, if it doesn't belong here, it will be something p-adic. You have no possibility that could be an automorphic. Okay. But for every point, yes. Okay. And okay. So that is the idea of an inequality that we have some objects are moduli spaces of automorphic representation. This is the concept. Okay, so the picture is something like that. Okay, so this is good to see. So the weight space is something very nice. The square or cube, it's something very, mysterious. So the mysterious is the eigenvariety. And in fact, these objects are very difficult to understand. We don't know. In the case of GL2, there are still some mysteries. GL2 or cube, in fact, in this case. The eigenvariety there will be an eigenformula will be of dimension 1, but still have a lot of mysterious questions about it. And still, if you prove, in fact, in this case, if you look at the singularities, still there is, we don't know if you take a modular form of weight 1. A special model with one, we don't know how many irreducible components we have. There are some conjectures, but still we don't know. So imagine for GL3, GL4, it's very mysterious. And singularities are very important in arithmetic because this kind of points sometimes belong to characters that being used to some big group, and you want to understand what's happening there, but okay, appear more irreducible components, difficult to understand the information. So that is kind of in the subject we try to understand this kind of points. And it's very interesting because the eigenvarieties are, I think, one was started like in 72, for example, by Hida, no, by 72%. And Hida and 86 make a very, start construction better. But there was a hole between 86 until 96. 10 years, there was no much advantage. Well, amazing. Still in the case, PL2 made more advantage. But then still 96 to 2008, we can say 2011, then they start general construction. So we can say the last 15 years, the construction of eigenvarieties is much well understood using different methods. Covariant homology, singular homology. But even now, for using covariant homology, there are a lot of works by Boxer Pironic, are very interesting to understand. And it's trying to study some interval structure behind and have a lot of important applications in the language programming. Okay. Okay. So we have this from the last 15 years, we have these objects to study them. So the similarities of them still is very open subjects. And I think that in the coming years will be more about it because they're new applications. But it's not called still the Q or Q is very active. Okay. So some examples that I want to mention, for example, if G is the case of the second section I was explaining, this result of with Dimitro and George, what we needed to obtain our theorem, one key part of the proof was to prove that eigenvariety at our point is egal over the weight space. We proved that, and that allowed us to deform everything that I said before. So we can say that the start point of our proof was prove that it's egal. And then we were able to construct, to resolve the theory of that. Some interesting situations when you take F, imaginary quadratic field, and you make the same process, you take the restriction of field. This situation looks similar, but they are totally different. In fact, in this case, the capital part of the eigenvariety is very mysterious. And when we tried with Williams in 2001, we tried to understand the capital part, and we are less mysterious. But even that allows us to take an application. Okay. The non-capital part, the non-capital is a work in progress with this balance first PhD student. And we are trying to study the non-capital part, but it's a little bit surprising because the non-capital part looks much simple than the capital part. I mean, the Hilbert equation is kind of the opposite. Okay, so now to finish my talk, I would like to look at the GL4 case. Okay, so I hope that the last previous slide gives you an idea of how we use the eigenvarieties in the Hilbert case to prove this here taking their derivatives. Yeah, the one. And what we are, so as I told you, for the eigenvarieties are very active now, but still there's a lot of stuff to do, and the GL4 case is very not very developed. I would like to spend something that happened here. It's very interesting because you have in the GL2 case or this totally real case or this case, for example, you have you look at the eigenvariety, and in all the components you have a statistic dense set of classical automorphic representation. So you look at the eigenvariety, everywhere you have these red columns that correspond to algebraic automorphic representation, so global classical ones. So they are dense in the whole eigenvariety. But in GL4 situation or the case of imaginary quadratic that I told before, it's very mysterious because it actually doesn't happen that you have components of the eigenvariety that you expect that the classical points are not dense, or dense. So in the GL4 case, or GL6, GL8, we study all the GL7 situations. We try to understand the situation and we obtain some results that I would like to share with you now. Okay, so let's see the other one. Oh, 10 minutes, okay. Let's see an automorphic homological cascaded automorphic representation of GL4A. Okay. I hope now that you have an idea what's in your adjective from the previous slides. And the weight is a weight of a couple of 4 elements because the torus is GM. Okay. And but some results that Barrera and Wallace and Gardner is that the weight of this kind of automatic representation is very restrictive. Because in the case that it's unitary, you have something like that. If not, you have one more tweak that you can ignore that. Something essentially something like that, the weight. So you have no 4-dimensional weight space that we are interested. You have the 4-dimensional, but if you care just about that automatic representation, just here you have something 2-dimensional. So that we will consider just this 2-dimensional part of the weight space, and we call again W. The eigenvariety we call XP again. This is eigenvariety, but consider that it's a piece of the other one. It's not the full eigenvariety, it's just a piece that we were interested for. Okay. We know that the reducible components passing through pi are dimension 2. All the reducible components are dimension 2. We know it's proved by Hansen and Newton in 2017. But doesn't mean that the classical points are everywhere. So just we're saying that the reducible components as a rigid variety, they are dimension 2. So maybe we can have one isolated point, maybe, and the rest are just p-adic. For p-adic. Okay. The definition is, I will explain what we care about it. What we care. So, there is something that I explained badly. At the end, I will explain what I explained badly. Okay. Our classical point is a point that corresponds to automorphism. And what we're saying till now. So we care about classical points. So we look at all the classical points in the eigenvariety, we take the statistic closure, and that gives you a subvariety. And the reducible components of this subvariety is what we call the classical points. Okay? I will do a picture in a few moments I will let you do a picture in a few moments about that, but not keep going. So you take out the automorphic representation, you have some points in the eigenvariety. So but you have not one point. So I shift a little bit in the second part of my talk, but because we need to choose one special point of that automorphic representation. So let's explain it. So firstly, what we're expecting is the first equation, and all the classical families come from JSP4. You know that JSP4 is very close related. What is inside of the other? So you have line of naturality that relate the representation of one group to the other in this. Okay. So we will suppose that our automorphic representation comes from JSP4, and we suppose that it's unramified at P. That is what's unramified. Now I will come back to what I need to explain. So the evaporative group that play a role in this business is the element of GL4 that P such that will take more P's upper triangular. Okay, so it's just the part that under the diagonal are everybody's multiple of P. This space has dimension 24. So that gives you 24 points on the eigenvariety. And the points are described in this way. So you take the automorphic representation and you take an alpha that is a system of eigenvalues appearing in this complex space. Okay. So as the dimension is 24, you have 24 points attached to the eigenvariety, appearing in the eigenvariety. The conjecture that we have is we try to understand these 24 points, and we're comparing with JSP4. So what we obtain is that the expectation is that these 24 points are classified in 3 classes. One having no dimension in classical families, the other one having 1-dimensional classical families, and the other one having 2-dimensional classical families. So recall that these points live in 2-dimensional irreducible components. So some people will have something like that, no? You have the point here, this is the second class of point, for example. And this red point will be the classical points appearing. And we say that in the second situation, they are organized in something 1-dimensional. Okay. And the rest is are just coincidental. The other that having pretty low. Okay. So yeah, I think it's a little bit vague, but let me explain the theorem and the ideas of time. So the theorem that we proved with Andrew Graham and Chris Williams is that take a point of these 24 points of that automatic representation. With the first step that we proved that in general, that if you look your points and you consider the classical families passing through it, you consider just the families coming from just before, and the dimension is smaller or equal than the expected one. So, for example, if you start writing the first equation, you have no deformation in classical family. You have just purely a fundamental deformation. Remember that the first equation is when the classical families are beginning at 0. So this will be dimension is more equal than 0, so you have no deformation. What it proves is that, we prove here that if the weights have satisfied this condition, that's called regular, that allows you to take advantage of some L values, and non-values function values. And P phi tilde is again not critical slope at P, then we prove that there exists only one classical family comes from just before and have the right dimension. Okay, so to finish, the ingredient of the proof is we classify the point, you put 24 points looking at just before at nice points, which we prove that the eigenvarieties is down there, and then we take advantage of this nice point and we move between these points using reality. And that gives you this theorem. To finish, one remarks is that this work has interesting connections to the relative Lagrange problem with study periods related to a function. We exploit them, expect that we will have much more information to this very relative Lagrange problem, which is very active now. Secondly is that we work with more general because we get to the 6. Oh, thanks a lot. That was what I want to say.